Thank you, Guanan, for the introduction, and thank you for the ISDA online organizers for having me. Today I would be talking about more on the technical aspects of how operational centers could assimilate more observations by accounting for spatially correlated observation errors. And this is the work I've been doing as a part of my postdoc in Reading here with Sarah Dance, Alison Fowler, and other colleagues from ECMWF, Met Office, and the Department of Metrology. So I would just like to start by motivation of why do we care about spatial observation error correlations. It's because operational centers, they only utilize a part of available observations. You have a lot of abundance, you have abundance of observations, but they're not really able to utilize all of them. Let's say, for example, you consider AMSUA observations, which are a microwave temperature sounder, which provides the sounding of from the surface to the stratosphere. And they're also one of the most impactful, instruments. But the operational centers utilize like about 40 to 50%. So these are assimilated at ECMWF. And what about the rest of observations? They are just simply discarded because of, let's say, a few of them are discarded due to quality checks, quality control procedures, and some of them because you don't account for the observation error correlations. So if you don't account for observation error correlations, here on the left-hand side, you see an observation location from an overpass of northwestern Europe for AMSUA observations. What happens is that when you don't account for observation error correlations, you have to apply some sort of a spatial thinning. So you have to take out observations, and in the end, you would just have a sparser sampling of them. So here it's the operational thinning, which is applied at ECMWF, which is around 125 kilometers. So this means you have one observation per 125 by 125 kilometer grid boxes. So for this area, you have a total of 147 observations. And you also have to do some error variance inflation. You inflate the diagonal entries of your observation error covariance matrix because you're not accounting for the correlations, and then you have to sort of downgrade them in the sense that you give less weight to them. Whereas if you account for the correlations, you have a denser assimilation of observations, so you can use more of them. So this is for the 31 kilometer thinning, essentially using all of the observations. And then in that case, you also treat these observations not as independent sources of information, because now you're accounting for the correlations. So you are able to optimally assign these observation error variances. And what you result in, you get a sort of a 5-fold increase in the observation density, at least here. But what are the challenges? So the observation error correlations can be included through the non-diagonal entries of the matrix R. If you recall the 4D Varcourse function, you have the observation error covariance matrix, which you use as an inverse of it, because when you assign some observation errors, the higher the observation errors are, the less trust you have on the observations, and vice versa. And why is it not done? Because, well, if you just look at a single cycle within data assimilation, you have millions of observations, and your matrix R, the observation error covariance matrix, would be of the order, let's say, 10 to the power 7. And it's not computationally feasible to do a matrix inversion. You could even try with a 10,000 by 10,000 matrix. It would take you ages because it's really computationally expensive. And also, there's another thing, that R changes with every data assimilation cycle, because you also change the observation sampling, because you have quality checks and then you have some bad observations, you have to take them out. So R is also not fixed, so you have to do the inversion for every cycle. And also you have lack of efficient fast numerical techniques, which you could which might allow you to do this kind of inversion. But there are some existing methods, such as the Cholesky decomposition, but this is usually done for accounting for the interchannel and vertical error correlations. So here the observation error covariance matrix would be of size, let's say 300 by 300 or max 1000 by 1000, because the entries would be just the vertical levels, or the you say interchannels, or the channel numbers. There is another approach, which is called the diffusion operator, which tries to solve a diffusion equation on an unstructured mesh. The mesh would be just, on the observation locations, and you solve it using finite element. And as of now, I've heard that it has been recently implemented in the JEDI framework. But for our purposes, for in our study, we are not really going to look at it because it's kind of complicated for sort of observation types where you would expect to have simple correlation structures as you would have in our case. And I would talk about these two, about Cholesky decomposition in particular, in the coming slides. So the aim of this study is to investigate the implementation of a correlated R, so accounting for the correlations, using fast numeric techniques in an idealized data assimilation setup. So what kind of observations we are considering here? Again, the AMSUA observations in all sky conditions. So the observations are assimilated regardless of what atmospheric condition they are in. And in our recent, we had a recent paper where, we tried to estimate these in these conditions, AMSUA observations in these conditions. And what we also found that the correlation length scales, so the separation distance between any two observations till which the correlations are significant, they lie between 75 to 150 kilometers. And we also found that the correlations are usually stronger for tropospheric channels. So in the areas where you would expect to have clouds. And the observation error covariance matrix is expected to be sparse. So by sparse, I mean, a matrix which has only few non-zero entries, given that the footprint of MCA is around 50 kilometers at nadir. So that means you would expect to have one observation correlated with only a couple of observations, not many. So in that case, you would expect R to be sparse. Okay. Yeah. So the problem we consider here is a non-cycle, single-step, preconditioned incremental 3D var. Well, I haven't written the full cost function, but this amounts to solving this linear system of the form S delta Z. So delta Z here is just an increment equals the right-hand side W, where S is called the precondition Haitian, and as you might be aware, B would be the background error covariance matrix, H would be the observation operator, and also here the square root of B is just the control variable transform which we apply to precondition a system. And at the end, yeah, D is here the vector of departures, where it's just the difference in the observation minus the state in the state variable in the observation space. Yeah, so we just consider a model domain of over Central Europe, so 0.25 degrees, which amounts to a state vector of 6,500. And the model variable which we have considered is temperature, let's say. And the background error covariance matrix is generated using this second order autoregressive covariance function, which is just, let's say, an exponential function with some fixed background error standard deviation, which is usually used for temperature, so around 0.1 Kelvin, and also operationally used background error correlation length scale of about 80 kilometers. And on the right, you see the observations. So these are the observations not taken from the operational thing, but rather from 71-kilometer thinning, because now we want to assimilate more observations, right? So the observations come from the METOPSI channel 5, AMSUA channel 5. So it's a tropospheric channel because that's where we found more correlations. And these are the observations which come after the quality checks. And also you see the color scheme that assigns those are the error standard deviations which are operationally assigned. So the range of those standard deviation is from 1.5 Kelvin, which is usually under clear sky conditions, to 3.7 Kelvin, which is under cloudier conditions. And these standard deviations are assigned through the observation error modeling, which is done at respective centers. So we had data from both ECMWF and the Met Office, but for simplicity, we just using here data from ECMWF. And how do you also model the observation error covariance matrix? again, we have done it using a weighted average of the first order and the second order autoregressive covariance functions, and these are their respective length scales, which we found just using just fitting a function on the correlation estimates here in black. So these are the estimates which we found before in the all sky conditions, and we just fitted a function here. And this is the function which we are going to use to get our R matrix. And that's how, by using the function, you get an R matrix of this form. You could see what we have also done is that we have assumed that all the correlations which are less than 0.2 are set to 0 because we consider them as negligible. And also, because we are removing some information, we are also kind of, changing the structure of the matrix. And a big assumption, not theoretically, I mean, covariance matrices are supposed to be symmetric, positive, definite. And for that, we apply some sort of reconditioning to improve the conditioning of the matrix. So you add some small increment to the diagonal entries. It's also called ridge regression. And with a small increment, we get a condition number of around 7,300. So you also see R has a nice structure. It's a banded structure. So you see, by banded, I mean, the error covariance values are just, they're only non-zero along the diagonal. And as you go far away, you have only zero entries. And it's also sparse. As I said, sparse meaning you have very few non-zero entries. So it's around 97% sparse. And the color scheme indicates that the covariances values. So these are dependent on also the assigned standard error deviations here. Okay. Also, we also need departures. So the departures are generated using these the canonical references, De Hozier, and also recent work by Hu and Dance, where you just take the difference in the observation error and the background error, which is mapped to the observation state by the observation operator. And the background errors and the observation errors are generated by just taking a random Gaussian type of distribution, where the background error would have the covariance of P, and the observation errors would have a covariance of matrix R. And the observation operator H here is for every observation, it does the bilinear interpolation of the four neighboring model grid points. So this is one of the errors which we generated, and you could see the background error lies between 3 sigma, so 3 times standard deviation, -3 to 3 sigma, and also same for the observation error. Now, coming to the minimization. So as I said initially, when you do a preconditioned 3D incremental y, it comes to solving a linear system of the form S times some increment S delta Z equals W, where S is your preconditioned Hessian and W is the right-hand side. Usually, since the matrix is supposed to be symmetric, positive, definite, conjugate gradient method is applied. And within this conjugate gradient, you have to do, for every iteration, you have to do a matrix vector product call of the form S times Pj. So Pj is just the conjugate gradient direction which you obtain within, in each iteration. So you need calls to matrix vector product of these form. And as you see, S is this big looking composition of matrices. So for that, you would need to compute, if we look at this part of the matrix, it involves computing R inverse H square root of B times the vector Pj, where we can also assume that this quantity is equal to Q. So that means it involves computing, let's say, Z, which is equal to R inverse Q, and which could also be written in another way of solving a linear system Rz equals Q. And that is where we would need to use a fast numerical technique, because the main computational constraint was having these inverse of the observation error covariance matrices. But another, we might need to do another solve, which involves, computing the right hand side vector W, because it also involves a matrix vector product of the form R inverse D. So you would also need to use a numerical technique there. And what kind of techniques we got? So as I discussed initially in my slides, there's one widely used called Cholesky decomposition, which would be a benchmark for us. So instead of solving this R times Q equals D, you would try to factorize R in terms of a lower triangular matrix. So by lower triangular, I mean matrix which has only elements below the diagonal terms, and the upper terms are zero, and same for the upper triangle. For upper triangular matrix, all the lower entries below the triangle are zero. So you try to get the factorization of that form, so L transpose times Q equals D. And then when you have this reduced system, you solve it by using backward and forward substitution, because if you have a matrix of this form, you just substitute the last value here, and then you keep back substituting it until you get to the point, and then you do the same for a lower triangular matrix. But this becomes computationally expensive as the order of the matrix R increases, because that would also imply doing a lot of floating point operations. So there are other ways of doing Cholesky, which is one of them is called sparse Cholesky decomposition. So what it does is that
Rishabh, there's 2 minutes left, just let you know.
okay. So I'll try to just, so you have sparse Cholesky, you have which gives you sparse factors, and then you have spike algorithm. So I should go quickly. We use conjugate gradient with 10 realization of observation terms. And what we found is that Cholesky takes a couple of minutes, whereas sparse Cholesky takes only a few seconds. So these are some of the increments which we see, and also we show how the benefits of having non correlated observation errors accounted for. So you see a non-diagonal R makes only sharp small increments, whereas a diagonal R gives you very large geographically widespread smooth increments. And the increments are again done by just doing a back substitution of the control variable. In terms of the power spectrum, you see the non-diagonal R makes larger corrections at medium and smaller scales, whereas when you see the green dashed line, these are also for the 10 realizations. You see when you do a lot of inflation, you are trying to put little confidence on the observations, so you are making very little changes to your analysis increments. Whereas when you account for the correlations, you make appropriate changes on all the scales, on the small scales, also on the large scales. But in the end, the idea is when you have a non-diagonal R, it provides smaller and more optimal increments. So for conclusion, operational centers describe a large fraction of observations, partly because observation error correlations are not accounted for. And these correlated R can be implemented by using fast numerical techniques. And so the idealized DA experiments which we perform with the MCA observations, they show improved analysis increments when correlations are accounted for. Whereas if you don't account for the correlations, you get larger increments, which you wouldn't want, because you go with the linearized assumption. The smaller the increments are, the better your tangent linear approximation is. So the sparse Cholesky decomposition also substantially reduces the computational cost, because as I said, when I did the minimization, it took only a few seconds compared to a couple of minutes for when you use just a standard Cholesky. And the ongoing work is trying to implement both for HSL, the one which uses sparse Cholesky factorization, and another algorithm called Spike, which is only for the banded matrices, specifically built for that. So I would like to do for a larger scale problem on an HPC cluster to see the differences in approaches, because this was just an experimental setup. And then also compare with the benchmark based on the timing of matrix vector products, changes in iteration, and retention of scales in the analysis increments, like I showed in the power spectrum and the analysis increments as well. Two more important things would be when you have, because I just consider a very small area, if you have large area, how would you solve this whole problem when the observations are distributed across multiple processors? So you would have some observations assigned to one processor, other observations assigned to other processors. So one way of solving would be to, take overlapping regions, because then in that case you don't have to communicate, but in that respect you're also solving a larger system. So you're solving a bigger matrix here, you're solving a bigger matrix from the observations here, and so on. There could be another way. So as I showed you, the observational covariance matrix is of this structure. Another way would be just, taking the diagonal blocks along these regions, so you don't account for the coupling between them, and you just make an approximation and see how much, you lose accuracy if you treat them independently. So yeah, that's all from my side, and I would be happy to take any questions.
Yeah, thanks, Rishabh. And there are already a couple of questions in UPad, and I think probably we don't have enough time to address all of them, but you can always type the answer in the
Yeah, I
UPad.
thought I really exceeded my time, but yeah, okay. Thanks
But
for
the
the
first
reminder.
question, maybe you can answer the first question, is from Chris. How computationally costly is it to compute the distance between each pair of observation locations? In particular, how will this scale from a localized experimental area to a global domain?
So if I understood, the first part of the question is, I don't think it's very computationally expensive, because how you compute the distance is using the great circles distance, which is, I'm not sure how expensive it is, but in my opinion, it shouldn't take much. But sorry, I couldn't get the second question.
The second is like, if you, how will this scale from a localized experimental area to a global domain if you expand
Yeah,
your...
so that is something which I was talking in the conclusion, that if you want to, apply this in a global domain, you would rather, considering a small section, you would consider the whole globe, and then you would have to divide it into small, so it's like a domain decomposition. So you take very small subdomains and you solve them in parallel, and that's where you would have to assign the observations. Let's say there should be a limit to it. So you assign some observations to one processor, and then you compute your part of our matrix and you solve it, and then you try to do the communication. If you want to do the communication, if you don't want to do the communication, you would have to make approximations like these, where you just run them in parallel and you don't care about the entries here. So that is something which we are looking next. This is part of our ongoing work. So yeah.
Okay, so there are also questions from Robin, Ashish, and Anthony, but probably do you want to address the answer that are answered in the UPad?
Yeah, all right. Yeah, that would be fine.
Thanks, Richard.
Yeah.